Let me now describe a simple test that Alice and Bob can perform using local measurements and public communication that will convince them that the two qubits are indeed coming from a source that generates truly genuinely entangled state of this type. So Alice and Bob, remember, they are good quantum physicists, and they do know that this particular state will give you correlations not only in Z observable but also in X observable. So we can write it that Z tensor Z is equal to 1. The average value of Z tensor Z is equal to 1, but also the average value of X tensor X is equal to 1. Just to be sure that we understand this expression, this is a way of quantifying correlations that Alice and Bob will see. Let me explain what I mean by this expression. So the average value of A tensor B. Now think about A and B as two observables, one associated with whatever Alice is going to measure, and observable B is what Bob is going to measure. Now, suppose they perform those measurements, then the outcome are, call it small a and small b, with a certain probabilities. So quantum mechanically, we calculate this average value as by taking trace of the state that two subsystems are in, so rho in this case, and multiplying this by A tensor B. So this expression will give you the expectation value of A tensor B, but we know that this is equal to, if the outcomes are labeled by small a and small b for Alice and Bob respectively, then we have some probabilities, joint probability that the outcome AB will appear times the value of A, value of B. But in our particular case, our A and B are +1 or -1, so we have two possible outcomes on Alice's side and Bob's side. So you remember that the eigenvalues of the Pauli operators are +1 or -1. So in this case, the product AB will be equal to +2, sorry, will be equal to +1 if A and B are identical, right? So if we have +1 or +1, so outcome +1 will give the product +1, and outcome -1 will also give us +1 here. And this product will be equal to -1 when the outcomes will be different. So this expression really means that we have here the probability that the two outcomes are the same minus the probability that the two outcomes are different. So PS minus PD. So in this particular case, when I write expression like this, that means that I have PS equal to 1, the probability that they are identical is equal to 1, of course, then this term is equal to 0. So this means that I have perfect correlations. The outcomes are identical. And when I write this expression here, that means when Alice and Bob choose to measure X observables, so if they choose to measure XX, they also get identical outcome. As it happens, the other preparations, when they do the calculations, if you were to do calculations, if you choose to do calculations of the average values using this density operator, that will give you Z tensor Z average value equal to 1. So the correlation in Z observables are identical as in the scenario number 1, but the difference is here that if you take the average value of X tensor X, that is equal to 0 in this particular case, which you can easily check. So if Alice and Bob then check the correlations in X observables, they can distinguish between those two preparations simply because they have different density operators. So how would that work? How would this test work? The best way, the simple way to do it would be for Alice and Bob to choose independently from each other for each incoming qubit, whether to measure Z or X. So for example, in the first case, if gives 1 qubit to Alice and 1 qubit to Bob, and Alice and Bob secretly, without telling each other and then completely independently from each other, decide which observable to measure. So in this case, they decided both of them decided to measure z. For the second qubit, as it happened, both of them decided to measure x. It may happen, of course, that for the third round, Alice chooses to measure x and Bob chooses to measure z, and the fourth possible case is where Alice chooses to measure z and Bob goes for x. If they do this, they register the values, and later on they communicate in public. Of course, in order to find out what are the values of the correlations ZZ and XX, they have to reveal the outcome. So they communicate in public. So Alice will just say to Bob, "Hey Bob, for the first round, I measured Z and I got +1." And Bob says, "Well, you know, I also measured 1, I got +1, well, that's good. We should have perfect correlations here." So they go to the second round and Alice says, "Hey Bob, you know, I measured X." Bob says, "Yeah, I measured X as well. And what did you get?" "I got -1. Alice says, "Yeah, I also got -1, so that's good." And they then consider the third round, and Alice says, "Oh, I measured X." And Bob says, "Well, I measured Z." In this particular case, they don't expect to see any correlations whatsoever, so any outcomes are possible. We can write this this way. So Z tensor X is equal to 0, and the average value of X tensor Z is equal to 0. And also in this particular case, this is equal to 0, and Z tensor X is equal to 0. So they go on through the all rounds, they reveal what they measured, they compare data in public, and then they can evaluate the average values of ZZ at XX, ZZ and XX. If they see that the average value of ZZ and the average value of X tensor X is equal to 1, then they are confident that the source of the two particles that they measured is genuinely produces them in genuinely entangled state. So Eve is completely excluded from the picture here, and therefore she doesn't know a priori the outcomes of measurements that Alice and Bob will get if they were to measure this in the Z basis, for example. So this is good, except that you may say, where is the secrecy? Everything is revealed in public at the end of this protocol. Yeah, that's true. So for now, I just described to you a way for Alice and Bob to convince themselves that they got particles from the truly entangled state, because this particular state is the only one that will give you the correlations, the average value of ZZ, Z tensor Z equal to 1, and the average value of X tensor X equal to 1. So that's the only state that will give you perfect correlations when you choose to measure in Z basis or X basis. So another way of saying this is that this maximally entangled state is stabilized by Z tensor Z and X tensor X. So that's fine, but we have to work a little bit harder to just turn this into the key distribution. So what we are going to do in the next step is we are going to interspace the test for the origin of your qubits with not touching some of the distributed qubits and turning them into a secure cryptographic key. So that's our next step.